Recall our earlier design procedure. Specification is where we write a specification for the behavior of the function. This could be textual or in hardware description language. Formulation is where we define the truth table of the circuit or a set of Boolean equations that define the relationship between its inputs and outputs. Optimization is where at the circuit level we want to minimize the number of logic gates that we require. May need to do this several times. Technology mapping is transforming the logic diagram to a new diagram based on the available implementation technology. Finally, we verify the correctness of the final design. It's important to note that larger designs can be difficult to verify completely. For complex systems, we tend not to apply this process to the system as a whole. Rather, we use a divide and conquer technique known as hierarchical design. Here, the circuit is broken up into blocks. We use the design procedure on each block and then interconnect them. If a block is a bit too large, we can always break it into smaller blocks. It's a bit like playing with Legos. Let's take a look at an example. An equality comparator is a circuit that compares two binary vectors to determine whether they are equal or not. And for the 4-bit version, the two inputs are two 4-bit vectors, A and B, with index 3 holding the most significant bit. The output is a single variable E. It is 1 if A and B are equal and 0 if they are not. You may be familiar with the 1-bit version of this circuit that's pictured over on the right-hand side of this slide. If we followed our original process, we would get a fairly sizable truth table. In order for A and B to be equal, though, each position for A and B must be equal. We can use hierarchical design here and use 4 1-bit comparator circuits labeled as MX, an additional circuit ME that combines the 4 results. For bit position I, we define the circuit output N sub I to be 0 if A sub I and B sub I have the same values, and N sub I is equal to 1 if A sub I and B sub I have different values. You can see the equation for this along with its circuit diagram. By using a hierarchy, we can employ 4 copies of the circuit from the previous slide. Its output is 1 only if all N sub I values are 0. You can see the equation for this along with its circuit diagram. In these diagrams, you can see the hierarchy without the connections. There are a couple things to note here. 1, hierarchy reduces complexity. You can see that 3-2A is simpler than our diagram, and 3-2B is even simpler. The leaves on these diagrams are primitive blocks. Reuse of blocks is an important aspect of hierarchical design. In Part A, we can see 4 copies of MX, but we can simplify that in Part B to reflect the fact that we only have to design one working MX block and then duplicate it 4 times. A regular circuit is one that permits it to be constructed from copies of a reasonably small set of blocks. In contrast, an irregular circuit has no such repeatability. We can measure regularity as the ratio of the number of primitives in the final circuit to the total number of blocks in the hierarchical diagram, including primitives. Larger the ratio, the higher the regularity. For our 4-bit comparator circuit, the ratio is 21 to 11. Modern processors contain hundreds of millions of gates. They're not designed at the gate level, though. While this chapter focuses on lower-level blocks, there are blocks of intermediate size that are known as functional blocks. These functional blocks provide a catalog of digital components that are widely used in the design and implementation of more complicated integrated circuits. Thanks for watching. I've kept this one fairly short. We'll look at the technology mapping in the companion lecture.